So this is the second video I'm going to show you guys on some more modern type, advanced physics type stuff. And this time we're going to look at relativity. Again, we'll be doing this in my class. So this will take us like an hour and a half to get through, but we'll try and do a rest job so you guys can see a little bit of what relativity is about in with your remote learning. Not ideal, but we'll see what we can actually do here. So there's two relativities. There's general relativity and there's special relativity. We're going to start with general relativity, proposed by Einstein like almost over 100 years ago, and we'll look to see what it's about. Okay, so where general relativity applies is about gravity and stuff like that. So there's also special relativity, which I'll show you guys next, which applies to objects moving with generally constant speeds and that type of stuff. And general relativity is more about accelerations and more specifically gravity. You know, it's the first real big theory about gravity since Newton. Okay, so the great thing about this, a lot of it's very story-based, and now you don't need crazy math to appreciate it and that type of stuff, which is great. So I'm going to take some of his classic stories, analogies, and I've sort of put the cron twist on them a little bit, and we'll see what we can do. Okay, so let's start with this. Here we have a ninja in an elevator, and there's a Jedi out there using his Star Wars force powers to help him out. So suppose you're in a falling elevator, so you feel weightless. Of course, if you're in an elevator, you'd feel weightless, sort of floating around. Okay, now suppose a Jedi sees you falling and he slows down the elevator. So he uses the force to slow the elevator at 9.81 meters per second squared, and then he continues to accelerate it upwards at 9.81. Okay, of course, when he slows the elevator, you would go into the floor and then you'd feel pressure from the floor as he raises it up. Since you can't see outside, there's no windows, nothing, all you would think is the elevator's been fixed and you just feel gravity from the floor as usual. Okay, because you really can't see what's going on because there's no windows. So because of this, gravity and acceleration are actually equivalent to each other. So you just think the elevator is fixed and gravity's working like normal, no big deal, but it's actually the Jedi accelerating the elevator upwards. And because of that, the two must be equivalent. Now, this is different than what you've generally been taught because you've been taught that gravity is a force, where Einstein comes along and says, no, actually, gravity is more the acceleration, not the force. Okay, so very different perspective. All right. So try this one, another one. Suppose you got a spaceship, you got two ninjas. One of the ninjas has got like a laser pointer, and he shoots the laser through the window of the rocket ship with the other ninja as it is accelerating upward really quickly. So suppose you're in a spaceship accelerating upwards, somebody at rest shines a laser through the window. Now, the two of you would see would be very different. Of course, the ninja shooting the laser would just see the laser beam go straight across. But for the ninja inside of the rocket ship, of course, we're talking about the rocket ship accelerating crazy fast. By the time the laser goes from the window to the other side of the spaceship will have moved up, which means the laser will actually hit the other side of the spaceship below where it went through the window. Okay, so if you're inside the spaceship, you would actually see the laser beam do something like that, curve down and hit below. Now, if the rocket ship was moving at a constant speed, that line would be straight. It'd be a straight diagonal line. But since the rocket ship is accelerating, it would actually look curved. So as you accelerate, the beam will hit lower than the window in a curved shape. Since the beam bends due to the acceleration, and acceleration and gravity are equivalent to each other, gravity should also be able to bend light. And it's not because it's acting on mass. So acceleration can cause light to bend or look like it's bending. And if gravity is just another acceleration, it should be able to do the same thing. So this eventually leads into what is often referred to as the space-time continuum, where in order to find something, you need to have the x, y, z coordinate of where it is, as well as know what time it's going to be there. So time is the fourth dimension. So you need 4 pieces of information to find something. And of course, you've probably heard of space-time continuum like in video games and movies and TV and that type of stuff. But it was one of Einstein's key ideas for how this all works. And the whole idea of the space-time continuum is one of Einstein's big ideas for how things work. And most people think of it sort of as a flexible fabric, which was one compressed extra energy, and the Big Bang released it. People think about this flexible, fabric-y type stuff expanding out, making the universe and carrying everything along with it. And when you guys took grade 9 science, you guys did an astronomy unit, and it's this expansion of this space-time fabric type stuff carrying the planets and stars with it, which is causing the universe to actually expand. So The idea behind gravity is pretty simple. When you have something heavy, mass causes this grid system, this space-time continuum system, to bend. So when things fall towards a star or planet or something like that, they're not actually trying to get to the object, they're just following the space-time continuum. So gravity is the result of a mass bending this space-time fabric. So objects fall into the dimple that's actually made. This falling is just the object trying to follow the bent lines of the continuum. So that's basically how things move, is they follow the lines of the space-time continuum. And if something bends those lines, you change direction, just the way it is. Okay, the common analogy for this is, somebody standing on a trampoline. If somebody stands on a trampoline and you roll a marble across the trampoline, the marble will curve towards the person, not because it wants to go to the person, but because it's following the curvature of the trampoline. That's the basic idea. Now, if you expand it further, even light has to follow these guiding lines. So everything has to follow these guiding lines. And this is one of my favorite little pictures for something like this. Got, I don't know why, but two ants with lasers, one with the red laser, one with the blue laser. Each of the ants would see the other ant's laser. So the guy shooting the red one is going to see the blue. The one shooting the blue is going to see the red. They will both see the red laser light. And you can see the space-time continuum between them is bent by something really heavy mass. So they both see the exact same thing, but the difference is the blue one actually shows the direction the light would actually travel to get across. It wouldn't go straight across like the red one is, because it can't skip over the space-time continuum like that. It would follow the blue line. So they both see each other. They see the same type of thing, but the blue one actually shows the correct path light would actually take. So the whole idea of light always going in straight lines is very far from the truth. So proof number one, we can actually see starlight behind other objects due to what's called gravitational lensing. So there's a classic thing for gravitational lensing where if you've got the Earth and you've got a large galaxy or something in the distance, and between that is another galaxy or something like that, well, you shouldn't see the far galaxy or star that's on the far right, because the light can't go directly to the Earth because it gets blocked by the thing in the middle. But we can see it because the light that is going just above or just below gets curved around the thing in the middle, and then it hits us. And of course, we trace things back in a straight line. So when we get our images that look like this, so those things on the left and the right, or all the way around, those are actually images of things that are behind the thing that's in the very middle, that dark thing that's sort of been blacked out a little bit. That's the thing in the middle. And the stuff around it are images, enhanced images of stuff that's actually behind the object. It's called gravitational lensing. So the idea is, if you have the sun in the middle, you got the Earth on one side, and you got a star on the other side, if it's directly on the other side, we shouldn't be able to see it. We shouldn't get any radiation from it. But the energy that goes straight to the sun gets blocked. But the energy that's going just beside the sun gets curved around the space-time continuum, and we intercept it, but then we trace it back in a straight line, and it appears that it's on to the left of the sun. Okay, so they actually did an experiment for this years ago where they had a satellite go on the opposite side of the sun and shoot radiation beside the sun, so to speak, and there's no way we should have been able to get the radiation, but we actually did. So a satellite simulated a star's radiation, and we got the exact same result of what is actually shown in the diagram. So it's in the exact opposite side of the sun, totally blocked, but the radiation, which is a form of light, got curved around because of gravitational lensing and the sun bending the space-time continuum. So in 2015, so only like 5 years ago, is space-time or gravitational waves were verified. This is one of the things that was predicted a long time ago by Einstein and others and stuff like that, is you've got some kind of crazy things like black holes or neutron stars, and they're moving, whatever. They could literally make ripples, just like bobbing up and down in water, ripples in the space-time continuum that would wibble wobble back and forth. So the idea was you got these two things out there. I think their neutron stars were orbiting around each other or something like that, or black holes. In the picture is black holes, and it sends these ripples in space-time. They use split beams in order to look for changes in the beam paths, and sure enough, they were detected in 2015. So this is predicted by Einstein from major black events, or big events like black holes and stuff like that, and neutron stars, and the ripples are verified. And then 2019, they of course got images of an actual black hole, and you can see the light around the black hole, but a lot of that light is actually coming from behind the black hole, from what's called an accretion disk. So once again, the whole idea of gravitational lensing and light bending around a heavy mass and that type of stuff. And it was shown, 2015, gravitational waves were verified. And 2019, being able to see the image or the light from behind and around the black hole, and you see the distortion of the light to get that ring shape, is because of gravitational lensing. Okay, so of course the black hole is the ultimate thing for space-time, where you dug too far, basically, into the trampoline, so to speak. If the mass is large enough and the hole is deep enough, the continuum fabric might actually tear. That's the basic idea behind a black hole. And Einstein and others predicted what it's a black hole and all that kind of stuff. Lots of people have worked on it and studied it and that type of stuff. Okay, and that's not a real picture. It's just an image of what one could look like, of course. So realistically, if you go inside, you're going to be ripped apart. Nobody really knows necessarily what happens to the energy for sure. Some people think it's a wormhole idea where black holes can actually link parallel dimensions before. We talked about the parallel dimensions with the duality stuff I showed you a little bit. And some people think you can actually, pop out on other sides of the universe, and space-time can be bent in different shapes, and they might actually lead to pathways and to other parts of dimensions or our universe, and that's where the idea behind a wormhole kicks in. But many people just believe that if you go, you'll just die. I mean, you'll be converted to pure energy, and a whole bunch of other bad things are going to happen to you. But what actually happens, nobody actually knows, and there's a lot of other cool things that can kick in with this as well. Okay. Now, Einstein died in 1955 before he could fully connect this to other things. It's part of what's called the unified field theory, which is still one of the greatest things that people are working on. And it was originally based, though, on a static universe, or a universe that wasn't actually expanding. And he introduced what's called the cosmological constant. And it's often referred to as one of his biggest blunders ever. But then it was shown, of course, the Hubble's law and Hubble's research that the universe was actually expanding. Now, of course, there's also dark matter, which holds things together, and dark energy, which is also connected to this type of stuff. And it's really interesting that our universe is expanding and things are being held together, but it doesn't seem to be enough stuff out there to actually hold things together. So another big part of this is the whole dark matter and dark energy thing, because when our galaxy is spinning, but with our galaxy spinning, it should be flying apart. There's not enough stuff to actually hold our galaxy together, and this gravity must be coming from what we refer to as dark matter, and the dark energy is even overpowering that. So we are able to only see a very small slice, or interact with a very small slice of the energy and matter universe to actually explain what we're actually doing. So it could have connections to duality, parallel universes, and all that kind of stuff. It doesn't mix well with the quantum mechanics or the really small stuff, and that's where string theory kicks in. You've probably heard of that before, especially if you want Big Bang Theory. And it's a really simple idea, sort of, that there's these little microscopic strings, and the resonant frequency of these strings produce the basic properties of mass and charge, and basically every measurement that we do. And it's because of the resonant frequency of these vibrating strings of energy, and that's what all of our interactions with are with reality. So that's the basic idea behind string theory. It sort of ties these things together literally. So that's kind of neat. But it's really cool how it's a really different look at how gravity works and the consequences, and we've definitely shown that there's a lot of validity to it with the gravitational lensing and that type of stuff. It's really, really, really neat. And even can connect to other things. For example, with the parallel dimensions with duality. When you guys did basic forces, we looked at how weak gravity is compared to things like electric forces and magnetic forces. We looked at that type of stuff. Now, one of the ideas is maybe because between the basic forces, maybe gravity is so weak in comparison because some people think that gravity might be a field that actually links parallel dimensions together, and it actually travels through different dimensions. So whatever we have is actually the diluted version of gravity because it's seeping into other dimensions. And maybe the electric and magnetic forces are so strong because they're locked in our dimension, but maybe it's the gravitational ones that seep through other dimensions, and that's why they're so weak in comparison. So there's lots of theories and lots of ideas, and lots of videos you can watch on YouTube about this type of stuff, which are awesome. So there's just a quick, very brief, summarized view of what general relativity is about. Next, we'll look at special relativity. And again, in regular class, a lot more detail, a lot more descriptions and stories we go through, but this is a little toned down version for you guys.